Good morning. Um, a warm welcome to the Kathegalu, Vigyana Kathegalu at the Bangalore International Center. We are really happy that our collaboration, which we started a couple of years back, is going well. We have had excellent speakers and lots of audience coming in for many of the talks that we had here. So I'm really also thankful to the Bangalore public for responding so well to these science talks. And I would like to start by introducing Professor Subroto Mukherjee as a very unique researcher. So he is, of course, has a hugely successful career in plasma physics, and particularly in applications of plasma, in various applications. How do you take the knowledge that we gain about plasma physics and use it for various applications? And this culminated in him, of course, growing as a scientist in various roles. He's a member of the Academy of Engineers. He's also recognized in various fora. He got the first Booty Foundation Award in plasma physics. So that's as a scientist. He was given the responsibility of a separate center, that the Institute for Plasma Research, which is India's most well-known and the almost only center dedicated entirely to research in plasma. He was given the responsibility to lead the Plasma Applications Center. It's called FCPIT, and he was doing that very well for a dozen years. And remarkably, our connection happened on a very different time. I mean, we met a few months before that, but one fine day, he had to move from a career which he had all set to take charge of a major responsibility for the LIGO India project, which is a frontier project coming up in India, which is for detecting gravitational waves. And he happily took it on, at a day's notice. And I'm so grateful that scientists of such caliber, willingly took up national challenges and worked for it. This is the spirit which I think needs to be kind of applauded, appreciated, and also amplified. Because often, we have our own research goals, our own glory, is things we want to achieve. But what makes a difference at the national level is to be able to set that aside, to take on a role. And he's done a fantastic job in that in the last 5 years. We had a talk by him at RRI yesterday, which you can find in the our YouTube channel. Probably it's already there or it should come out soon. And recognize what what science means. Of course, to grow individual science, the freedom of science, but also the responsibility that most of the science is funded by the people, and leave no opportunity where you can use your scientific expertise to do something that the nation wants. So I really feel, here's a amazing example of someone who could set aside 12 years of a very successful career at the peak of his career to move and say, okay, no, I will lead another group. So he leads the LIGO division currently of IPR. And so he was nice enough to spare time to give one talk on LIGO yesterday. And today, to you, he's going to talk about something that often is not talked about, are these technologies in plasma physics. Plasma physics is not as widely spoken about. I don't see kids talking about, oh, let's do plasma physics. But you'll get a sense of what you can do and what transformations you can make in the society using plasma technology. I would not come in between you and the talk, so let me welcome Subroto to give his talk.
So good morning to all of you. Thank you, Tarun, for the introduction. And it actually happened that entire career of mine from 1989 onwards till about 2017 end was only this, plasma applications. And then, of course, a major turn came that I was asked to take care of the LIGO project, one of the parts of the LIGO project. And that is on the gravitational wave detection. Yesterday we had a very nice interaction with faculties at RRI. But this is a subject which is close to my heart. And I thought that for a popular lecture, I'll keep it in such a way so that you understand what is plasma. As Tarun said, plasma is not very popular. You understand what is plasma, how it can be used, both at a giant level as well as in a very small level, and how the society has to accept it. So first of all, these lines, these words, I'm going to come to these words at the end again. Environment friendly, plasma of course, and industrial and societal applications. Okay. Now in India there is only one institute working on plasma research, Institute for Plasma Research, which is an autonomous institute or an aided institute under Department of Atomic Energy, Government of India, located in Gandhinagar, Gujarat. And so most part of the talk is actually about what IPR has done, because that being the only institute in the country and its association with various other people throughout the country in popularizing plasma-based technologies. These technologies are extremely popular, especially in Europe and USA, even in Japan also, that there are certain things which are only allowed by plasma techniques. But however, within India, it is still not a mandatory thing in that sense. Now, to understand the institute, I am going to come out the work detail. But we have two tokamaks. I am going to come about what is a tokamak at a later stage. These are basically reactors or something which looks like a torus in which a plasma is made. And so the major activities of the institute are tokamaks for nuclear fusion, then technologies for nuclear fusion, and plasma technologies for societal benefit. Now if you open a dictionary, a standard traditional dictionary, not the Google, just our old earlier dictionary, right, look at what is plasma. There are two things: fluid part of blood, lymph or milk. Like plasma is given to a patient so that he recovers. So that is one part. Another is a high temperature ionized gas that is electrically neutral. Now, nowadays most of the lights are actually LED lights, but even a couple of years back, we had these tube lights, these long ones, and you switch it on. There will be once or twice it will blink, and then you see a nice light inside. Now, if you break the tube light, you don't see anything. You see only a glass, a long cylinder, which has a white coating in it. So the place which was giving you light actually has nothing. Basically, the matter goes to plasma state. There is a gas inside it at subatmospheric pressure. And at the end, there are two filaments. When the bulb on the tube light goes bad, you can see some red light at the corners. Basically, there were filaments which will emit electrons. And once that electron emission happens, the plasma sustains itself. Plasma gets formed. So that is a fourth state of matter. I'll come to that, what are the other three states. So this matter going from a gas to a state, which is ionized, because you see a current flowing, so your meter starts moving whenever you switch on a tube light. But at the same time, it is electrically neutral. You can still touch the tube light. Not at the ends. If you touch at the ends, you get actually 230 volts. But that is a 230 volt from the line. But otherwise, you can touch the glass in between. So the matter is still electrically neutral, but it is conducting electricity. That means electrons must be flowing from one end to another end. So this part is very clear. So a matter being ionized, conducting electricity, normally it was not conducting. A tube light otherwise will be just like a tube if you don't give 230 volts. So this particular name of plasma was given by one of the scientists. There you can see Langmuir, this person. How do I go to that place? Langmuir? Anyway, we're able to see the name of Langmuir, Tongsan Langmuir. Langmuir actually gave the name plasma because the first time he made a nitrogen plasma, it looked absolutely red in color. And he thought that this is much closer to blood plasma in appearance. He gave the name plasma. So he used this term plasma in 1929, and since then we all call plasma. Moreover, how do you characterize a medium? Now normally we tell, if I have to characterize a medium, I'll put a thermometer to measure temperature or something. But if we are telling, if we have some disease, we go to a hospital, we never to tell that I am going to the hospital to get myself mischaracterized. We tell diagnosed. We never use the word characterized, but actually we are going for a characterization. So what happens is that even in plasma also, we use the term diagnostics, plasma diagnostics, to basically characterize the plasma. So two things came from the medical side, plasma word and plasma diagnostics. Okay. So there are three states of matter. Just for example, ice, water and gas, that is the steam. These are known. You take a solid, which is ice, heat it, becomes a liquid at 0 degrees centigrade. You heat it more,
Do you want to point us out?
Okay. So you take, say, the ice at 0 degrees centigrade, you give energy, it becomes a liquid, which is water. At 100 degrees centigrade, it becomes a gas, that is, the steam is formed. Then you go on giving energy to the system. So this steam, at one point of time, the electrons inside the molecule, outermost electrons, they will pick up the energy and they will go out. So now you have one ion and one electron. And this will keep on happening as long as you supply energy. And that is the matter going to plasma state. However, there are natural plasmas. The sun is in plasma state. You have the northern lights, the auroras as it's called. We all go to Sweden, Denmark and other places to see that. Lightning is matter in plasma state. In fact, the spark that happens, suppose you put a fridge or an air conditioner and you switch it on, there's a small spark which happens. At least for that time, the matter goes to plasma state. So basically, the gap in between gets ionized, transiently, but it gets ionized. There's a very famous experiment called Miller-Urey experiment. What he did was, he put all these gases, and these are gases like methane, ammonia, water, and hydrogen. These are all the gases which are not organic in nature. These are inorganic gases. He put all of these gases and then had a very high voltage in these two electrodes and made this entire set of combination of gas to a plasma state. And when everything was switched off, he found certain amino acids which are got formed. So basically it is even told that amino acids are basically proteins or whatever which build the life, that it is probably this type of inorganic gases in the presence of lightning in the atmosphere probably started the amino acids, which are the building blocks. Probably life started. There are various theories about how life started. One of them is this one. Now a little bit about plasma. I have tried not to use any equations to tell as simple as possible. So it is a quasi-neutral collection of charged particles that exhibit collective behavior. Now, I may have one electron here and one ion here in this building, in this hall. I will not call that as plasma because these charges are moving independently than each other. By collective behavior, I mean that, let's suppose we as a group, we work together. Or as a group, we do something, which individually we may not do. Like suppose if somebody tells you to walk 5 kilometers, unless you don't want to do, you will not do. But suppose we tell, no, we have to protest against something, or we have to walk 5 kilometers for some cause, then we'll walk. We'll not think about 5 kilometers. So this is one is a collective behavior where the behavior of this entire group of atoms or ions would be different than their individual behavior. So matter actually shows collective behavior. Quasi-neutral means it is nearly electrically neutral. It is electrically neutral to start with. In plasma state, it is nearly electrically neutral. Maybe 1 or 2 particles here and there can get lost. That is among a huge number of particles, say 1 million particles. Maybe one can get lost here and there. So plasma is characterized by certain lengths called Debye length, then number of particles called much more than 1, and plasma frequency. These are basic characteristics. Now, how do we treat plasmas from a scientific viewpoint? That we tell that when a gas is there and the gas is energized, it goes to a plasma state. So a large part of the gas, large part may be still small, it may be still less than 1%. So if there are 1,000 atoms, only 1 may get ionized. But if there are 1 million atoms, and for every 1,000, 1 gets ionized, so basically from 10 to the power 6 is 1 million, and out of that, say if 1 in 1,000 gets ionized, I'll get 1,000, 10 to the power 3 number of ions and electrons. If the number is even more than the neutrals, then I'll get more and more. So basically, the ions and the electrons in the plasma, I can consider them as 2 separate fluids moving around each other. And they have the same density because the matter is still electrically neutral. However, they can have different temperatures. Now, this is not easy to understand because if they are moving together, that whether they can have different temperatures, the answer is yes, because electrons are much smaller. So if they will get energy more from whatever field is giving energy, and ions are being bigger, they will get lesser energy. So their temperatures would be lesser. And because these are charged particles, ions and electrons, you can describe their motion using Newton's laws and Maxwell's equations. If you know Newton's law and Maxwell's equation, it's fine. Otherwise, just accept it. That Maxwell was a Nobel laureate. He gave 4 equations, and that is part of electromagnetic theory. And we use that to tell motion of charged particles. And of course, Newton's law comes along with it. Now, the collisions with unionized neutral, out of suppose 1,000 electrons, 1,000 neutrals are there, 1 gets ionized. So this is the collision is between that one and the remaining 999. So collision with unionized neutrals can be added in the momentum equation. So there is another equation which describes motion. You can add them, and if there are some sources and sinks, so something is preparing, something is going away, you can add it in the continuity equation. So Maxwell's equations, Newton's laws, momentum equation and continuity equation would describe any plasma. Whether it is sun or it is this tube light or it is that spark, you can have described more or less with that. So now here comes the talk. I will actually divide part of the talk towards energy generation and part to layman's application, very down to earth applications. So if the plasma will have as 3 species, one is the gas which gets ionized to produce electrons and ions. So if the electrons have one temperature, I call it T, the gas Tg and Ti. So these are the 3. Many of you who may be knowing a word called thermodynamic equilibrium. That is all the constituents of that matter which is in thermodynamic equilibrium can be described by one temperature. Like suppose if I ask you what is the temperature of the room, answer is say 24 degrees centigrade. So 24 degrees centigrade is the temperature of the oxygen molecules, which is about 20%. And 24 degrees centigrade is temperature also for the nitrogen, which is about 80%. So these are 2 separate species. They are separately available in around this one. However, both have exactly same temperature. So this is the matter in thermodynamic equilibrium. But in plasma, it is not necessarily like that. With these 3 can be completely different. If this one is much, much more than the gas and the ion temperature, usually called as cold plasma. You can actually touch them. This is a tube light. You can touch it. Another is hot plasma, where all 3 are nearly similar to each other. So you must have heard terms like plasma welding, plasma cutting, which is now very standard industrially used. This is more on this type. So if you put plasma technology here, there's a wide number of applications, and I'm going to come to some of these applications at a later stage. Now, if we try to make just a simple plot of density, density is number of charged particles per centimeter cube on the x-axis, and temperature in y-axis. This tube light is somewhere here. Lightning is here. Whereas magnetic confinement fusions, core of the sun, thermonuclear weapons, they are about here. Now, air has a density somewhere very close to this, 10 to the power 19 over here. So, air density. But look at this temperature, and this is in degree Kelvin. So, this is 10,000 degree Kelvin is close to 1 electron volt. And this is 1000 and this 1000 electron volt. This is 10 to the power 6 electron volts. So, these things, magnetic confinement fusion, thermonuclear weapon, the sun's core, they are very close to atmospheric pressure in terms of their the percentage of basically the number density, and also the temperature is very high. Yes.
You said air is 10 power 19, but are they charged particles? Air is essentially neutral.
No, air is neutral. So air is only given that the air density is sitting somewhere here. It is not to tell that air is ionized.
Below that you have number density charged particles.
No, this is only to indicate that air is sitting here. It is not telling that air is a part of this. So these are all parts. The air would be somewhere here. This is only telling that. Air is actually not ionized, but you can ionize air also. Like lightning is one thing which ionizes air and propagates. So like that way you produce plasma, and plasma has nearly equal number of electrons and ions. Now you can make a wide variety of plasma. Now I will tell about this one. The nuclear fusion, where it basically starts with a helium, it starts with the isotopes of hydrogen, that is tritium and deuterium. They would fuse and produce a helium and a neutron. And these neutrons carry a large energy, which actually one will slow down to get electricity out of it. And this is the science behind nuclear fusion, which I am going to come a little bit later. Obviously, like any star which is emitting light of its own, has the nuclear reactions happening there, nuclear fusion reactions, and they emit the light which we see, as well as the other things. Now, if we have a charged particle, as I told, of density is very close to the sun's density, the core of the sun, which is needed to make hydrogen isotopes, deuterium, tritium come together. Remember that the moment their matter goes to plasma state, these are like positively charged now, and they would never like to come because they will repel each other. So they have to be made in a vessel which is actually infinite in length, because any finite sized vessel will have ends, and in the ends means basically you have to put something to end it. So this plasma will go and hit it. So how do we make it? Means without any end or without any boundary, is that you take this plasma in a magnetic cage. So these are all coils. In most cases now superconducting coils. So this is like the plasma doesn't have an end. And it is floating in space. Now as you know, if a matter is a conductor and close to an ideal conductor, it will not like magnetic fields, it will like to go away from magnetic fields. So these being magnetic coils which produces the magnetic field as needed, the plasma will try to go away from each one of them, and hence it will be a plasma which is in this like a torus, but it is like levitated in space. It is just being held in space. But it is very easy to tell that one can do it, but plasma being more intelligent finds some space to escape here and there. And this device is called as the tokamak. Like there are 2 tokamaks in our institute in Gandhinagar. They are medium-sized tokamaks. But to have nuclear fusion reaction like hydrogen isotope, deuterium and tritium, and generate neutrons out of it and then slow them down to electricity. It was realized by the scientists in the fusion community globally that it requires so many technologies to come that it is very difficult for one country to master it. So 7 countries, China, European Union as one country, India, Japan, Korea, Russia, and USA, are building a nuclear fusion reactor in south of France because it's just too complicated. It is like actually making a sun on earth, actually, with all parameters of sun. So this device called as ITER, International Thermonuclear Experimental Reactor, this is being built in South France, and this is how the schematic looks like. And this is the person standing here. So to give you an idea, this is like a 30 meter, and this is about 30 meter, and this is the person standing. Now India is about 10% partner. So the partnership is like this, that about European Union is 40% partner, and the remaining 6 are approximately 10%. So it makes 100%. So what are the things which India will be giving to this one? These are various things like this cryostat, the neutron shielding, radio frequency heating, particle beams, cooling water, cryo and power supplies to run this. But this is about 10% of the work. And what we need to learn by participation are these various types of magnets, blankets, then the fuel cycle, how do we convert it from neutrons to energy and other words. So these requires a large amount of Indian R&D. My institute is involved, as well as various industry participation is involved, as well as we are still learning the ones which are in red. So plasma applications. What I told in the last 2-3 slides about ITER, it is a very promising, but it is highly complex in technology. You have cryogenic magnets, which are cooled by helium, so 4 degree Kelvin, keeping a plasma which is very close to sun's core temperature, like 10 to the power 6 electron volts, in that order, 10 to the power 3 to 10 to the power 6 electron volt. So you look at the gradient, one side is 4 Kelvin temperature, which is like minus 269 degrees centigrade, and then you have to hold something which is at 10 to the power 6 Kelvin. 10 to the power 6 electron volt, 10 to the power 9 Kelvin, in that order. So with very sharp temperature gradients, which is not easy to do. The secondly is that it requires superconducting magnets, requires magnetic fields which are very strong, like few Tesla magnetic field, in a very large volume. If one thing is making few Tesla in a lab in small volume, another is making in a volume which is like this. So there are many technological challenges, and ITER will one day will need some more time to be profitable enough to serve the society. At the moment it is getting built, and there are challenges which scientists are overcoming. The question is, are there plasma technologies that can benefit society now? By now means in the current time. And I'm going to talk of thermal plasmas and non-thermal plasmas. Like the one which I told, non-thermal is the tube light, usually called as cold plasma because you can touch it. So thermal plasmas, I'm going to talk of plasma pyrolysis, nanoparticle generation, and non-thermal plasma will be plasma nitriding, wound healing, plasma activated water, textile, and many more after that. So obviously now, because now we are coming to something which society or industry will get benefited, so comes the patents and technology transfers and all those things. So this is where institute is here. Now it may look like that I am quoting IPR in many places, my institute, but it is because IPR is the only institute in plasma research. So if we talk of anything of plasma, it finally comes down to IPR is linked somewhere. I mean within India. So plasma pyrolysis for waste disposal, and I will end with a video on this one, my talk with the video. So it talks of environment, energy generation. We are working on green hydrogen from waste, plasma nitriding for increasing life of tools, some textile treatment, plasma-based nanopowder production, as well as a wide other things like strategic applications. We are very strong collaboration with ISRO on thruster studies, plasma thruster and space plasma applications. Okay. So I'm going to first touch upon two applications of hot plasma, where electron temperature is very close to gas temperature, is ion temperature. And this temperature is much lesser, about 1 electron volt, and that's like 10,000 degree Kelvin. Around that, slightly lower or higher than that. Now waste. Now there is no need to tell what is waste. Luckily there is a glass with water, so it will not become a waste after I drink the water. Otherwise the plastic bottle becomes a waste the moment you drink the water. So either you recycle it or reuse it or make something else out of it. And if you don't do anything with it, it will become a waste, like what we have here. So this is an estimate which the government did, like about 1.4 lakh tons MSW per day. You may tell, no, it is much more than that, it may be 2 lakh tons per day, but it is in that order, lakhs of tons per day. It's only get transported from our homes or from factories to a dumping site. Then this dumping site becomes a small mountain, then it catches fire, and then a lot of things happen. So then it stays here, then we find a new dumping place, because the city has expanded, which may be another 20 kilometers. In another 10 years, that will have the same fate. So we have to somehow minimize the waste that we transport from the source, which may be our home or from anywhere, and process it as much as possible. And it is only at the last stage we destroy it in an environment-friendly manner. Like the tires are there, then various other parts. And also the body parts which are removed. There's a biomedical waste. PCB is an enormous big waste. We still do not have a very nice the policy on how to handle discarded electronic waste. Now,
What's that molecular structure you're showing there? The previous slide? The UV structure of the cell.
no, this is basically a general structure of a cellulose. So waste is everywhere. It's just a matter of if it is a water bottle, plastic water bottle, it becomes a waste in no time. So this is actually a Deonar. In Bombay, it is very close to Anushakti Nagar. It actually caught fire a few years back. And the fire and smoke was so much, even from the International Space Station it was visible. They could see things coming up. And then also in Delhi there is a place which caught fire. The reason the fire happens is that because this waste lies there and they undergo chemical reactions and they generate methane. And you can actually smell methane if you go near the waste. And that catches fire. Once it catches fire, it is anyway going to burn for a long time. So the best way to handle any material is that first is that you do not use it like what is here. You're using glass, that is much better. Then minimize, reuse, recycle energy. But at one point of time, you have to dispose it of. Suppose even if you take a plastic bottle, make it a bag, then that life is over, convert it to something. At one point of time, it has to be disposed of. Now, how do we dispose of? So we are going to propose that plasma is a technology which is there. Now, how does plasma pyrolysis work? Now, the word pyrolysis, you may be aware about, that is basically a combustion process. But combustion process always requires oxygen. If I burn a fuel, I require oxygen. Can I combust something in an oxygen-starved environment? By oxygen-starved means it is to be much lower. I'm not adding oxygen. If I add oxygen, I'll tell that, okay, it is combustion. I'm not adding oxygen. If there is some oxygen here and there, it's fine. So this process is called as plasma pyrolysis. And this you can do by plasma technique, giving heat or any other technique, provided you are able to give that much amount of heat to destroy very toxic molecules. So this is a primary chamber where a very, very high temperature is there. High temperature means 5,000 to 10,000 degree Kelvin, in that order. No air. By no air, I mean I don't add air. Pyrolysis process happens and there is no combustion. Again, when I tell no combustion means I am not adding additional oxygen or air to combust it. In the secondary chamber, we heat it to a very high value. Again, whatever gases come, and then we rapidly quench them. And we reduce the amount of dioxins and furans in the exhaust. So there are certain limits, it has to be below that. So this is our first plasma pyrolysis system, and as this is the Central Pollution Control Board officials who actually visited and gave us the permission to operate this machine. So this is all made in Ahmedabad, a very local company made. So that is also another thing, we cannot work on making an instrument which we have to import from outside. So if you think about a technology, we have to see that it gets made within the country, everything, right from controls, data transfer, controlling the process, as well as the measurements, all happen with locally. So these are made by a local company, and these are my friends, Chirayu and Vijay, who did this, and these are the CPCB officials. So this is a primary chamber which opens at a periodic interval, and one feeds the waste here. Inside there is this plasma system here. You will not be able to see that. From here it goes here, and it generates certain gases. They go up, and then there is a secondary chamber, this long one, in which it gets burnt at 1000 degrees. Then there are Venturi scrubbers and a secondary scrubber, which actually quenches them, and then there is the emission. So there are certain norms of the government of India. If you take a waste, you destroy it, this is what you can emit. So what are those emission norms? That you are allowed to emit these gases apart from water vapor and air. Carbon monoxide has to be below this number, NOx below this number, particulate matter below this number, and dioxin and furans, which are basically carcinogenic. Till now this is one thing. These are carcinogenic, it is below certain number. And this is actually very similar to the US norms also. US exactly has similar norms for waste disposal. And these are some of the numbers from our system. And it took few years for us, with various setups being demonstrated in various parts of the country, that these numbers are very consistent. So Central Pollution Control Board gave us the permission to use plasma pyrolysis based systems for first case was a biomedical waste disposal. So our main thing is that biomedical waste is actually anything, as long as it is connected within the body, it is part of the living person. But the moment some operation happens, something is removed from the body, it becomes a biomedical waste. And what gets removed is actually not very good. That is the reason it is removed. It may be a tumor or something, or an accident happened, something has to be removed from the body. So all that is one biomedical waste. The catheter and other things which go inside a patient's body, that is also biomedical waste. Even the gloves and other thing which the doctor or the nurse uses, all that is biomedical waste, including even the saline bottle. It is not a biomedical waste as long as it is not connected to the body. The moment it is connected through a pipe to the body, it becomes a biomedical waste. So this technique actually handles all those categories of biomedical waste. And my last slide will actually highlight that more. One of the possibilities over here is that this line, because this gas like carbon monoxide can actually it is actually flammable. You can burn carbon monoxide. So if you are able to do that thing in a very proper manner, you can have carbon monoxide as well as some amount of hydrogen also, which is called a syngas, and which can be fed into a generator, electric generator, and generate electricity, which we have shown. But however, for biomedical waste, we normally recommend not to use energy recovery, because energy recovery means you have to do a little bit play with the process parameters. Nanoparticle generation. Now, if you know, of course, everybody knows about nanoparticles, its presence and things like that. Now, if you remember, maybe 10-15 years back, our cricketers were using some cream when they were fielding in the sun and all those things. And they were actually white in color. They were visible. Now also they apply the cream, but the cream is no longer visible. The cream is still used. And that is because the particles which were there in the cream, their sizes went down. So there are various techniques of making nanoparticles. One of the technique is using plasmas. The reason is that if you use, so this is one of the setup. Now we have even larger setups and we transferred this technology for other applications. You can actually have an arc, and suppose I want titanium dioxide nanoparticles. So there will be a electrode of titanium here, and there's a high temperature plasma converting titanium to titanium atoms, and they will flow down. There's a thing which actually pulls it down in an oxygen environment over here, and you will get very small titanium dioxide nanoparticles. Now, titanium dioxide is used in many places, including even our toothpaste and these creams and everywhere. So this is one of the technologies to do. It can produce in large numbers, very fast. So this is what we have transferred. You can also use plasmas to do nano patterning on surfaces. So this is a surface in which you would first do a patterning on the surface, and then you put on the surface whatever you see, the spherical ones are basically silver droplets. So it is again been done, all are done using plasma techniques. So you first nano pattern a surface, and then you, on the top you put silver. And then there is one process which is actually named in the name of Sir Raman. That is so then if suppose I want to measure the presence of some chemical which is in very small quantity in the blood. It is so small that conventional pathology techniques would not be able to detect. But you want to detect that one. Suppose if I tell what is your the sugar, you will tell some number, everybody. But if you measure urine sugar for a person who is not diabetic, urine sugar will tell there is no sugar, 0. It is below their detective limit by the conventional pathology. Here if you do, it will tell you whether it is present or not. So this particular technique also we have done, we have measured the templates, and there are various things we are working with Tata Memorial Hospital on enhancing the signal for things which are very minute quantity, so that we are able to predict that this man would probably going to get this disease at some point of time in future. So after this I will come to some other applications which is in the other dimension, that is where electron temperature is much higher than the gas and ion temperature. Why it is called cold plasma? Because the majority of the species are gas and a very small number would be high. But these electrons would still be having temperatures of the order of 10,000 degree Kelvin or even more than that. But because their percentage or in the gas, in the overall thing is very less, hence you will not feel the heat. Like the tube light, you can still touch the tube light. The tube light doesn't melt when it is on. The glass remains as it is. So I am going to touch upon some examples of this one. Okay. Many of you may be having watches which were very popular some time back, the Titan watches, bright golden yellow color watches. And Titan is one of the first companies in India to use titanium nitride coatings on watches. It is not gold. It is actually titanium nitride. It's a compound. It's a cubic structure, as we see. And that coating sort of revolutionized the applications of plasma-based coatings within the country. So now, of course, titanium makes the strap as well as this part of the, and now there are various techniques. Like we have anti-glare sun glasses. The light which comes from the other side, even on the windows of the glass, you don't see the light. You see only a light, but you don't get the glare which comes out of it. So these are basically all coatings, and most of these coatings are done using plasma process, because you can control the coating thickness to such a level, like you require λ/4 wavelength thickness coating. You can precisely control it to that level. So we do a wide variety of coatings on very large areas. And we make also the instruments for doing that, so that when we transfer the know-how to someone, how to make it, we also tell him how to make the instrument of large size, because then only it becomes commercially in a scalable manner. So this is that plasma, the pinkish violet color around, and then this is that component, this is something which we did for the ISRO applications, called flexible foldable antennas. So antennas are normally rigid, but you can roll the antenna and then wherever needed you can open it like this way. So then there's a process for plasma nitriding, again for ISRO, for there all the gears and everything. So this we all made in-house, such systems, and we made this for ISRO for plasma nitriding technologies. This is one of the most successful technologies that we have developed at the institute. And it is very popular. There are companies even in Bangalore who has taken these technologies and have now making it on their commercial level for their usage. So what is this process of plasma nitriding? That we all have know about steel, iron and then chromium, nickel, these are alloying elements. So you take, if you are able to put a little bit of nitrogen and carbon, either both of them together or at least one of them, they will go inside and they will form the alloying elements of iron, like if you have titanium, a little bit of titanium nitride. If it is chromium, chromium nitride. If it is iron, iron by itself also forms iron nitride. But how will it go inside? If I take a component of made some steel and put it in atmosphere, it will remain like that. Maximum it can get say rusted, but how nitrogen will not go inside. So what one has to do is that one has to increase the temperature of this. By mean this is a physical temperature, heated to about 550 degrees centigrade over here. And these being metallic components, put it on a holder, like here in this case the holder, and bias it using a pulse DC with controls and everything, and measure the temperature. You'll find a nice plasma being formed around it. And in that plasma you put nitrogen and a little bit of hydrogen. This nitrogen dissociates N2 to N. And that N, because of temperature of 550 degree on the component, will actually diffuse inside and form this compound. Then as it cools, the compound is formed, it is present inside. And it increases the surface hardness of the component, typically by a factor of 3-4 depending on the material. So surface hardness increases, wear resistance increases, and corrosion resistance increases. For most steels, these three happen at the same time. If you take a cross section under a microscope, this is how it will look like. This is a very popular technology, and many a times we get within country some people who tell that we have got an order from say Germany, where they specifically said that this component has to be plasma nitrided. You cannot do with any other technique increase the life of the components. As you can see over here, this is one of the big reactors we have in our institute. This is actually a part of a turbine. It's about 220 kgs in weight, about nearly of my height, about 5.5 feet. Okay. So plasma activated water for sterilization applications. Now this we started about 5-6 years back. There was somebody from a hospital, and their microbiology head came in that they tell that they find two problems. See, normally hospitals, if you go inside, it's all air conditioned. Then you go to the ICU, it is also air conditioned, but even a slightly lower temperature ICUs. And they have to be cleaned, say, every day, twice or thrice, the flooring and everything. So what is the compound which is used for cleaning? Usually something like Lysol or something like that, some disinfectant. Now this are there in the system, in that room. They stay for a long time, these molecules. So he told that, is it possible that I will do this mopping and other things, but without using any chemical? So then we started looking at the literature, and we found that in South Korea, they are trying to activate water using plasma. So that is how it started. That can we activate water? The activation has to be such that it's not a permanent activation, without using any chemicals. By when I tell chemicals, I mean chemicals like which comes in a bottle and things like that. So this is what we do. We basically take water. This is only a lab setup. We have now much larger setups. And we use, this is a small plasma jet working at atmospheric pressure. We pass air is plain air, and then of course high voltage and everything. And it forms inside over here. This water gets activated after some time. By activated means you start with normal water, which is pH 7. And after doing this for some time, the pH starts become negative, lower. So 7 will become 6, then 5 and 4 and something like that. It typically becomes 3.5 around that. It will basically stay there. But the staying is not permanent. If you do this treatment, go to pH 3.5 and keep it in a container and measure after every 1 hour. You will see 3.5 will gradually become 3.7, then it will become 4 and gradually, and after 1 day it will become 7. The reason is that this water gets activated. So basically certain nitrogen and oxygen in their excited states, they mix with water and make the water a little bit acidic, like it is below 7. And then it interacts with the atmosphere, and again all these radicals recombine with them, so become air and again go away. So this is now a lot of work we are doing, and we find that sterilization of components which are actually used works very nicely, as well as what I told about mopping and other things. So we have filed some patents also in this. About 2 patents have been filed. And you can actually see there's some morphology of some cell. I don't know why it is not coming here. But basically, if you look at some cells, the control is like this. When you dip it in the plasma activated water, this cell wall actually breaks down. So this particular cells basically they do not survive anymore. And many of the bacteria and other things will not survive. Now, can I touch a plasma, a cold plasma? The answer is yes, because it's electrically neutral. And so this is one of my friends who first made the first plasma jet. So this is air plasma which comes out. So these are multiple jets. And I have a very young entrepreneur type friend who happens to be a faculty in Shibpur B Engineering College. Now it is IIEST. It's a university now. He told that we should start looking at applications for real human beings. All that we did was everything separate. So we approached BRNS. They somehow gave us some money. And he then went to PG hospital in Calcutta, known as SSKM hospital. It's a government hospital. And there we found a doctor, Dr. Sumit Sen, who happens to be someone who takes up newer ideas. And he told, okay, let us try to use. So did various initial trials, and then finally they did a sampling basis and told that, okay, we would like to apply on this thing, on patients. So this is this particular, for the doctor, this particular type of infection is happening in the patients in rural West Bengal, those who specifically involved in the paddy cultivation. If you have gone, you may have seen that they actually sit on the ground, basically which already has some amount of water. So some part of their body is actually in the water. And they will put something here and they will just go to the 1 feet. They put another one, they go 1 feet. So their body is, this part of the body is in water for considerable duration. And you see, their dress also is very less. Very up to this much only. So they get a fungal infection somewhere in the lower part of this one, or I'll show some other pictures, backside and things like that. So so this is a plasma jet which is coming out over there. You can feel it. You will feel as if somebody is picking you, something like that. So these are actual case studies. So this man came, it's about, in this particular case, it was argon and oxygen which was given. So he came, the doctor identified that this is a Tinea curcis, is the name of the, the fungus. Then he was given a treatment of some time, typically about 15 minutes or so. After 1 week he comes here, again a dose is given, and then after 2nd week, again another dose is given. And after 3rd week, this is the person. And according to the doctor, the fungal infection is not there. The skin may take another 1 year to come. This is without any medicine. No tablets, no ointments, just this treatment. So this is another case of initially and then after 7 days. So this is how it started, that same person. Then according to the doctor, this fungal infection is not there. So this is Abhijit, and this is done in the SSKM hospital. These are all done under medical supervision, so that the doctor tells, okay, you have to give him for this much time and all those things. So these are real applications, and then of course the funding agency tells now you do it for a large number of people, generate statistical data. Because finally we have to compete with the conventional treatment for fungus, which is basically ointment. And as you know that fungus infection never goes away. It only gets cured, and so that it comes back. The moment environment is suitable, it will again come back. So plasma technology is for textiles and sort of lamination. Now there is a wool called as Angora, Angora rabbit wool. I don't know whether you are familiar with this. This is a rabbit, very nice looking rabbits. They grow only in the sub-Himalayan region. They will die in this environment, even Bangalore environment. Only in sub-Himalayan regions that is there, like Kulu, Manali, and in that area. And their fiber, which comes this one, the hair basically, is very smooth. It is so smooth that if you take, say suppose this much amount is there, you take with your hand and you just do like this, half of it will fall away. If you take cotton of this much and do like this, nothing will fall. So cotton fibers have some friction among them. This doesn't have that also. So how do you make a dress out of this fiber? Because there is no friction. First you have to make a thread, then from the thread you make a dress. So this came to us from the Kullu Weavers Society. They told that is it possible to make something, this fiber, so that, but there's a huge demand for this Angora dresses. It's very fancy and very costly also. So we being scientists, we first started looking what is the problem. So we realized that if I take this hair and put under a scanning microscope, this will how it will look like, very smooth. These places are very smooth. So we told that let's try to do a little bit of friction on the surface. So like this surface, little bit up and down, but it should not be so much that our body feels that the friction. Like if I take a woolen sweater, you will feel that there's a, it interacts with the skin. So little bit roughness, so that these fibers can actually make 100% Angora thread. And this is the first machine that we did, made for Kullu Weaver Society. So basically you insert the wool, just like you take the wool and just make it fall like this way. It goes through a conveyor belt, which is this one. And inside there is a dielectric barrier discharge or a plasma at atmospheric pressure with air, and this is how the plasma column will look like. So it goes through this and it comes out from the other side. And there's a control and everything over here. So we did a wide number of applications and we transferred it to two industries who are now making this one. So it's a very, and then we use it for textile applications, for putting functional groups on surface and things like that. So plasma treatment of textile, these are whatever I showed earlier. This is now a much bigger machine, and which is put in man-made Natural Textile Research Association in Surat, which does this. So there are like various types of polyester things come, which is not easy to dye. So you have to activate the surface. So you put this sheet, which goes like this way through plasma treatment, comes out with certain functional groups mounted on it, like COOH or OH, which like certain colors, and then that gets added. And remember, this is again a dry process. There is no water or anything anywhere. You just have it, and what comes out on the other side is a very dry one. So this we developed. We have even filed patents around these systems, so that when we transfer to this, our idea of patenting is not to make money. It is that to protect the technology within India, so that Indian industries do not when they take the technology, they do not face a problem. At least within India, they don't face a problem because it is patented by us. So that is the main aim for us. So by conclusions, I'll tell that, as you can see for most of my presentation, what I have used is air, argon, electricity, very rarely water or something like that. All for destroying something or making a new type of material which is useful. So these are mostly dry processes, and so there is negligible residue. There is always some residue, but a very small amount. And even if there are some emissions, in most cases there are no emissions. Emissions are there, they are below the emission norms as per Central Pollution Control Board. This fourth state of matter as plasmas, it needs energy for its creation. Like tube light, you have to give 230 volts, some amperes of current for it to work. So I can switch off the tube light whenever I want. So in all the cases, if you want to switch off, just switch off the power, it will switch off. So whether it needs energy for, and hence is highly controlled. Even ITER, which is getting built, is also with the same idea. That okay, I want to stop, you switch off the plasma forming power, the plasma will switch off. Suppose you want to have a problem somewhere, you want to switch it off. It's not necessarily that you have to continue it. And these techniques that we have done, there's a large number of industrial and societal applications. I have shown only some of the applications. There are a wide variety of applications which are not described, like sterilization of medical equipments, then surface activation as an intermediate process, for drag reduction in vehicles. This is recently becoming this thing that as the e-commerce thing is picking up in the country, we will be having a large amount of big trucks, not the ones which we see inside the city, the big ones, transporting material from one place to another place. And they typically would go around 70-80 kilometers per hour when they're moving. And so this drag, how do you reduce? One is that you reduce it by aerodynamic design. You make the mouth a little bit longer. It is more like try to design it like a bullet train, or like say Vande Bharat, or like that way. In that, one is design. But if you use a plasma at a right place, at atmospheric pressure, the air which it comes, suppose there is something which is moving, the air will come, suppose it has a shape like this. A part of the air will go in this direction, and the part may be going near the wheels which below. Wheels you cannot do anything. Over here, it will go like this. Now if you want to reduce the drag, you have to make this air stream which is going like this, to like this way. So you will find vehicles which are being designed in such a way, many of our SUVs, that it goes like this, and then after that, at the end, it takes a little bit of turn over there. This is only to tell that this air, this stream, should go in this way. It should be as close as possible to the surface. If I have a plasma source over here, it will actually make it much more closer to the surface. Power is not a problem because these trucks have enormous power already present inside. You require maybe few tens of watts of power. So that is one, that improve nitrogen fixation in soil, dissociation of pesticides, clotting of blood faster. So these are other things also we work on, and all of them have some patents which are transferred to industries, or it is at an advanced R&D level. Some of our major projects, and I'll go to the next 2-3 slides on that. One is biomedical waste at Varanasi, which is done along with Tata Memorial Center and Varanasi Municipal Corporation, and plasma nitrating system to be operated in the GOCO model. I don't know whether you have heard this term GOCO model. Government owned, company operated. Many petrol pumps work on this model. Like it is owned by Indian Oil but run by a private company. So we are now making a very large scale plasma nitrating system, and we'll tell a company that you run it. He will pay some money to us, and rest is how he runs, he makes his own profit. The equipment belongs to us in that model. So thank you all for your attention. If there are questions, I will be happy to answer.
You mentioned there that it makes blood clotting faster. I thought the aim, like when you have stents and all that, is to knock off the clot, even for brain hemorrhage in terms
No,
of-
our application in mind is not to increase clotting when the blood is there. Suppose, like people above a certain age usually take blood thinners, ecosprin and those.
I'm taking.
Huh. Now, if there is a surgery, one has to happen. This person's blood is not going to clot very easily because he's on ecosprin or something of that kind. How will you clot blood? For a normal person, the blood clotting will happen in some time.
So they say knock off the ecosprin for
No. That is one. But suppose it's an emergency, you need to be treated. You're already taken that day's ecosprin. So what you do when a surgery has to be done, blood has to. So basically what you do is that have that plasma jet, as my friend showed for the infection. You just put it. It will clot much faster, typically 1/3 the normal time.
Thank you. And the other question I have is, in terms of application for ion engines for space travel, can you comment on that? And also a little bit on your gravitational. What does the future hold? Anti-gravity, whatever, however utopian it may sound.
Okay, now let me tell about plasma thrusters or ion thrusters as you are telling. ISRO has already made thrusters which are about 300 millinewton thrust. That has been tested and it is clear for approval for this one. At IPR, we are working on, we already made 100 millinewton thrust and we are currently working on 1 Newton thrust, plasma thruster, using a completely new concept called as helical plasma-based thrusters. In fact, already Europe has already mastered this to some extent, and we are also in the process of that. Plasma thruster would probably be used not for launch, but in your orbit corrections. So you will have 3 or typically even number of 4 of them to put the spacecraft in orbit, and if it goes to deorbit, again bring it back in orbit. So in India, there is a work on ISRO is doing in a very advanced manner. They call it the Hall effect thruster, HET. And we are working on about a few days means about a month back, a big ISRO team came to IPR and they are very keen to take this 1 Newton thruster actually for flight worthiness in a time scale of 4 years. So it has to undergo a large amount of qualifying test, 1 Newton, to make it flight worthy. One is working in a lab, but the moment you talk of space, your weight is the first restriction. How do you reduce the weight? Your power supply has to be miniaturized. It has to work. And you are taking the power from the solar panel. So your demand of power also has to be very less. So we are working on that.
Thank you for the presentation. I would like to understand about this plasma transplant, That is, there's in medical terms, there's a requirement of plasma.
That is that other plasma which I said in the beginning, part
Correct.
of blood and other. That is not is what I actually talked about.
No, but that is present in the body, right?
That is present in everybody's body.
No, what is the actual need for that actually?
That I don't know. As I know, it's part of the blood and it must be useful.
Okay.
That is not. This is what I'm talking about. Plasma
No, I
is
understood,
ionized.
but I just wanted to-
I know it is useful, and during the Corona time, many people were donating plasma to save lives.
Correct.
That got more popularity at that time.
Okay.
Can you say a little more about, the mountains of waste, how you're going to reduce them using plasmas? I
Sir,
didn't quite catch that.
Okay, so the main thing is that first of all, we strongly insist on segregation at source, which of course is everybody knows that one has to segregate. What can be composted, that is made fertilizer, like food waste and vegetables and all those things, should be composted either at individual level or at a society level, whatever it is, or regional level, to make fertilizers which are, or manure which is more environment friendly. The whatever cannot be combusted, then, and it cannot be recycled, that should be, if it is recycled, it's fine, let it get recycled. Then comes a time when you just can't do anything, you just destroy it. Not put as a mountain. That is where the plasma thing comes, because plasma is needing electricity to destroy something. So unless the economics support it, it will never catch up. So it is not that the municipal solid waste generated in our housing society has to go through plasma. We never tell that. It is when all options are lost out, then because it cannot be destroyed just because the environment doesn't know how to dissociate it. Like this plastic bottle. You can keep it outside for as many years, nothing is going to happen to it. So those things are the ones where the plasma should come into picture and dissociate with two very small molecules.
But where is it being used? That's my question. In an experimental, a prototype version or elsewhere, is the use of plasmas for this kind of waste disposal already there, at least at a prototype level?
No, it is there. It is there in
India?
In India. We have built this, the Rodra thing which I said in the end. This is coming up in Varanasi. It is for actual biomedical waste. Biomedical waste, you cannot do anything. It comes as a waste, it has to be disposed of. So
that's a very small quantity of all the waste, solid waste that's being...
No, that's what I'm telling. We should not aim to destroy any waste which comes out.
Okay.
What can be composted, what can be recycled must be done. This is my understanding. Otherwise, we'll be spending, like if I take typically a waste which comes from our kitchen, most of it is water. You will put heat only to make water to steam and go away. Water will not do anything. So it is better to go through a composting or a fertilization route. The biomedical thing, we have many biomedical plasma systems throughout the country. This one in Varanasi is a bigger one, 5 tons per day. And it is not one hospital. It is catering to all the local hospitals in Varanasi.
Good afternoon, sir. So my initial question was going to be about the IPR's work with ISRO regarding outer space propulsion system. But while you were answering that question, you mentioned that the solar panels are used to generate energy and that is used to make plasma. But then a doubt arises in my mind that the outer space is mostly consisted of plasma. So isn't it possible to use that plasma to generate that?
See, plasma is fourth state of matter and it conducts electricity. Those definitions hold for the plasma coming out from the thruster as well as the space plasma present in low Earth orbits and other places. But the density difference in a low Earth orbit, the plasma will have a density of 10 to the power 4 particles per centimeter cube. 1 centimeter cube is this volume, only 10 to the power 4 maximum. Whereas this plasma thruster, the plasma plume which comes out, it will be having a density nearly 10 to the power 13 per centimeter cube. Because a certain amount must come out with a certain velocity to give you the thrust to move forward. Just Newton's third law over there. So we cannot use that plasma, the background plasma. We have to generate this plasma, and that power has to come where? In space, the only place for power is the solar panel, which is there.
Thank you, Professor, for that insightful lecture. My question is more with regards to the hydrogen sector, because that's where I work. Is there any comments on where we're at with splitting water using plasma?
We have started working, it's still at the laboratory level. I can tell that much at this level. It is at the laboratory level. Our method of commercialization is like this, that unless we come to a stage where we are able to file a patent, because as I told you, we need the patent to protect our industry to whom we are transferring, not for our own this. So at the moment it is at a research level, a very small level. But we are using plasma for electrolyzing the water.
Thank you.
Thank you for the talk, Professor. I believe one thing you mentioned was you could use plasma to improve solar cell efficiency. Did I catch that right?
Yes.
Can you elaborate on that a bit?
Basically, the solar cell is made exactly like the way you have made the solar cell. But on top of the solar cell, you can have an anti-reflecting coating. By anti-reflecting coating means basically if a sunlight falls, it goes through this coating. And then when it wants to come out, it fits striking angle is more than that and critical angle, it will go back. So it will bounce back. So instead of going out, it is going to stay in over there, unless it comes to, it gets this. So this anti-reflection coating, typically in many cases that we have seen, it increases the efficiency by about 1 to 2% on top of what it already has. There are literature which supports this also. So suppose if you have a solar cell working at 20% efficiency, it will become 21% or 22%, which is actually a big number if you see in the long run. As well as many of the nowadays, though silicon solar cells are very popular, but there are articles on new solar cell materials and thin film solar cell materials over there. In fact, today there is an article about new material on solar cells which are being claimed by Indian Institute of Science. Just today morning I read. These are new, I think lead telluride and tin tellurides and things like that. So like that way, we can have thin film solar cells which are there. And in thin film solar cells, the plasmas play a major role in making many of these thin films. We have made a solar cell which in our institute, which has efficiency, which is about 5 to 6% efficiency, very low. But its absorbing layer is copper, zinc, tin, sulfur. The one which actually absorbs sunlight and make it. So there is no silicon at all. It's a non-silicon based multi-layer film structure. All done with plasma process. So your substrate actually moves in vacuum from this chamber to that chamber and all that. And finally a solar cell comes out. But it's still at 5-6%, not at a level to at a level to tell that it is a big success. But it's non-silicon based.
What's the application of this ITER?
ITER is basically the International Thermonuclear Experimental Reactor project being built in South France by 7 countries. And the main thing is to make a tokamak which will show that you can have more number of the neutrons that comes out, the number of neutrons, and come out with a very large energy. So the total energy, possible energy that you can recover is more than whatever energy you have fed in to make the ITER grade plasma. But it is a very challenging, very many front end technologies are being used. There are some delays also.
If that ITER is successful, then energy will be the whole planet will rely on fusion.
That I cannot tell, but what I can tell is this: if ITER is successful, that is what we all hope. Then the next thing what many countries would pursue, probably including India, is to make a reactor called as demo. And demo is going to demonstrate that you can commercially put power on grid using thermonuclear fusion alone. No fission, only thermonuclear fusion.
Thank you for the lecture. So one question was, you said there are some US fusion energy startups, right, who are claiming to provide energy back to the grid. So are they using the same technology as the ITER project?
No. They have claims which are different, and there's one called Helion Energy, and then there are Spark is another. They have sometimes configuration like the tokamak, but not necessarily working in the same principle. Sometimes even linear machines, they will make 2 plasma blobs come together, then mix them up, and then change magnetic field, go like this way. While it goes, it will induce, because it is like a charged particle moving, it will induce electric fields. That will be more than whatever you have put inside. But they are promising to put power on the grid in very short time scales, like 28, 30, like 6, 7, 10 years from now, which is very ambitious.
That is Boston, you're talking.
Various places. Boston is one of the places over there. Even there are people from Princeton labs who have gone and started. In fact, many of my friends in IPR who did PhD, they are now working in those companies. Like Tri-Alpha Energy is one company, Tri-Alpha, TAE. And they all have very ambitious claims. I personally believe when they're making a claim, it's just not for, they must have enough amount of success behind them.
did it for plasma generation.
I did follow what?
For plasma generation, what the ideal pressure of gas conditions?
It doesn't matter. You can make in atmospheric pressure to 10 to the power minus 6 millibar. You can make anywhere. Like this plasma jet, which is for wound healing. That's at atmospheric pressure. And plasma nitriding is about 1 millibar, like 1,000 times lower than atmosphere. Most of the plasma thruster working in space. Space is much lower vacuum outside. It's working there. So it's all a matter of how you use the electric field and magnetic fields to produce the plasma and are able to confine it appropriately. You need not even use a magnetic field in many cases also. So basically you have again tritium and deuterium type of material in a pellet, which is laser from very high power laser from all sides. Shine on it, it will explode because it got an energy. Matter goes to plasma state, the outer shell, it goes inside. And by Newton's law, the inside will get compressed. So that will go to fusion reactions will happen. Even laser fusion is also very successful. There are many claims on that. Still not at grid level, but definitely at a demonstration level, it is very successful.
So plasma state is induced as like a byproduct, or it's
no,
not necessary?
it is not necessary. It happens. The matter goes to plasma state because you have put a huge amount of power to, suppose this is a material, you put a huge amount of power from everywhere. So obviously the top surface will go to plasma state and then it will expand. So when it expands, the third lot is whatever is inside will get compressed. So that goes to the fusion level.
Oh, got it. Thank you.
And ultimately it will generate neutron and you have to slow down the neutron to get energy. That part is the same. Slowing down of neutrons to get energy.
And on that note, on behalf of the BIC, I'd like to thank Professor Subroto Mukherjee for explaining this strange material that's apparently used from everything from sunscreens to space travel.